All right. So welcome everybody. Today I'm going to be talking about my research that I'm working on under my master's thesis. My project is centered around bifunctional gold catalyzed monofluorination of propargylic carbon-hydrogen bonds. Obviously, I'll get into all that, what all that means, but I'm going to kind of just outline some background and then get into what my day-to-day kind of looks like doing my research. So the main objective is to develop a catalytic method to fluorinate sp3 hybridized propargylic carbons through CH functionalization or activation. Propargylic, that is this site here that is just alpha to the alkyne, just a fancy name for it. But yeah, the whole goal here is to develop a bifunctional gold catalyst that can both coordinate to the alkyne while also deprotonating this sp3 propargylic carbon, which is going to activate it, and then hopefully we can fluorinate from there, as you can see by the schema below. So I'm going to kind of go into a little bit of background here. So background behind fluorinated molecules, an estimated 20% of pharmaceuticals and 40% of agrochemicals contain fluorinated motifs. And this number has actually been increasing over the last 10 years. So organofluorine compounds, they have a lot of industrial application. Same thing with materials chemistry. It's also really big there as well. The carbon-fluorine bond is the strongest bond in organic molecules at 467 kilojoules per mole, just due to the very high electronegativity of fluorine, which gives it an extremely high dipole moment. And what that does is it actually gives unique characteristics to organofluorine compounds. So as I discussed before, the pharmaceutical industry, this here, lumateperone, it is a recently discovered schizophrenia medication. You can see it has a fluorinated arrow compound here. And then flupeniofenix, this is another new compound that is used as a acaricide, so it kills spiders. So it's big for agrochemicals and stuff like that. Both of these were synthesized in 2020. So like I said, fairly new. And you can see a lot of fluorinated motifs in this compound here. So definitely a growing industry. More specifically, when it comes to fluorination reactions, there's three different ones. There's nucleophilic fluorination, radical fluorination, and electrophilic monofluorination. So traditional methods, back in the 60s and whatnot, was a lot with fluorine gas. More recently, they've used DAST. So these reagents are highly reactive. They're not very functional group tolerant. They're a little dangerous to work with. Recently, they have developed bench stable electrofluorine sources. So select 4 for an example. That's this compound here. So like I said, they're stable. They're in salt form, and they have a lot of advantages as opposed to a lot of the more nucleophilic sources. They're much easier to use on industrial scales, obviously, because they're safer. And also they can help drive asymmetric fluorination reactions. And what I mean by that is stereoselective fluorination. A lot of the time, especially using F2 gas, you're just basically fluorinating everything. So it's a little hard to control. So these are a little easier to work with when dealing with specificity. So what exactly is CH activation? It is a reaction that cleaves a carbon-hydrogen bond and replaces it with a CX bond, where X can basically be anything. In this case, it'll be fluorine, but any really functional group can undergo CH activation. So apart from fluorine, the carbon-hydrogen bond is the next strongest at 412 kilojoules per mole. Therefore, to activate these, you generally need transition metals. And also, due to the frequency of carbon-hydrogen bonds in organic molecules, the substrate and the catalyst are extremely important in getting specificity, right? You think of an organic compound, it has tons and tons of carbon-hydrogen bonds. You don't want to activate all of them generally. You usually want specific ones activated and change into something else. So that's where specific catalysts, substrates, and stuff like that are really, really important. Most of these are driven by palladium reactions, especially the sp3 carbon hydrogen activation. But there's a wide range of palladium catalysts that are able to do this, as well as other catalysts, which I will talk about. One of the methods for stereoselective CH activation involves using transition metal catalysis to enhance base-assisted electrophilic substitution on pi systems. So what exactly does that mean? If you look at the scheme below, first you have coordination of the metal to break the alkene, and then you actually have a labile base ligand attached to the catalyst, so it's within the vicinity to achieve this CH activation. It's going to reform the alkene, give you this intermediate, and then because you just have a metal bond, you can usually just throw a functional group at it. It's going to create an electrophilic center, and you're going to get bond functionalization. You can see from the start, you had an alkene, there was a hydrogen here, you remove the hydrogen, and you're left with a functional group. So this is CH activation. The whole point of the base being attached to the ligand is it just being within the vicinity to deprotonate that hydrogen that is right there. If you just throw in an external base, you might be getting deprotonation at other sites, different CH activation. So this is kind of a good method of getting selective CH activation. So I'm going to dive into gold catalysis. So why gold as a catalyst? There's a big stigma around gold. You think that it's super, super expensive. It's actually a lot cheaper than some of the other catalysts. A lot of the palladium catalyst is cheaper than platinum catalyst, cheaper than that, iridium, rhodium, a lot of these, it's actually a cheaper metal. People just assume that it is really expensive. But if we're talking about alkynes, gold catalysts have very high electrophilicity towards them. The reason behind this, there's a couple of reasons. First of all, there's a strong sigma donor and pi acceptor interactions with alkynes. So 237 kilojoules per mole and 56 kilojoules per mole, respectively. So you can see a very, very strong sigma donor interaction. Because the antibonding alkyne orbital is high in energy for alkynes, it favors sigma donation, which, as we talked about, very, very high for gold. There is higher shielding as a result of lanthanide contraction and relativistic effects because gold's lower on the periodic table. Less shielding means lower ionization energy, which again is favored for this gold. And then in relation to that, the gold LUMO is 17 kilojoules per mole less energy than compared to silver. So it favors it as well. So yes, silver would be cheaper to use than gold, but you would probably have to double your catalyst loading, which would just make it more resource intensive and actually more expensive. So that's why gold is kind of the ideal catalyst when dealing with alkynes. So you can see here, you have your nu2 coordination to your alkyne. Under nucleophilic attack, you can activate it to an alkene. So this is a common gold catalyzed reaction. And then over here, I just have a model kind of depicting the orbital interactions that you're seeing. So you have your dz squared getting sigma donation from the alkyne, and then you have the back donation from another gold d orbital. So you're just getting a really, really strong interaction between the two. So that's kind of why gold is the focus here. So a little preliminary work behind my research. So I keep throwing around the word bifunctional catalyst. So what exactly does that mean? So in this case, these catalysts contain both a gold center and a free amine. So once the gold gets nu2 coordination, it weakens that propargylic carbon hydrogen bond, which is going to lower the pKa. And then that free amine that you have within the ligand, kind of as I talked about earlier, is going to be able to deprotonate that propargylic center. So this is kind of the, I guess, structure behind these catalysts. So you have your gold bound to a Y atom. In this case, this Y is phosphine. You have big steric groups. So what that's actually doing is it's pushing this backbone down, this amine, away from the phosphine and everything, and it's making it so you cannot coordinate directly to the alkyne. So this is a nice free amine that's not going to coordinate and kill the catalyst. So that's kind of the structure behind these, and there's been quite a, or not quite a bit, there's been a little bit of research based on these catalysts. So just diving in a little bit more here is kind of a full structure of the interaction that's going on. So again, you have your nu2 coordination to your alkyne, these big adamantyl groups, as I discussed before. There's limited phosphorus and carbon-2 rotation, just based on sterics from the adamantyls. And what's happening is it's pushing this carbon backbone, and then you have this nitrogen. Again, it's not coordinating to the gold, but it is right in the vicinity to deprotonate this propargylic center, which is what we want. And you're going to form an alene intermediate. As far as the catalyst itself, there's a lot of different modifications we can make to the ligand. So location of the amine, so right where the nitrogen actually is, if it's, has free rotation, if it's built into a ring. The size and nature of the R groups, so electron withdrawing groups, electron donating groups, something that's gonna, give the ideal acidity to deprotonate that propargyl carbon. And then the size of the backbone as well, right? Kind of relates to the location of the amine, right? We don't know if we want some alkyl groups, if we want, exactly the size of the backbone itself. So like I said, there's endless opportunities. So this research, it's a pretty open area of research. So work done by Wang, they used this catalytic method to generate 1,3-dienes through a double proton shuttle. So I'm not going to dive too far into this mechanism, but basically I just want to kind of highlight exactly what is going on. So you can see here, this is your free amine. So you have coordination to your alkyne, and then you have deprotonation of the amine as we talked about. And then this gives you your alene intermediate. And what's actually happening is you're getting a proton shuttle. So this center here is going to deprotonate the amine. So now you've gone from a hydrogen, propargylic hydrogen, and now it's on the other side. And then this process just repeats itself. So another deprotonation of the other propargylic hydrogen. And then again, the proton shuttle, which gives you your 1,3-diene product. So they just kind of showed that, yes, you can, when you're coordinated to the alkyne, you can deprotonate using these catalytic methods. So this was kind of the early work that was done. So expanding off of this, Li and Zhang, they kind of had a different approach. They wanted to introduce an electrophile, which can be attacked by the nucleophilic alene intermediate. And their goal was, like, we know this proton shuttle is going to happen, but if you can introduce a steric group that can restrict the proton shuttle, the electrophilic reaction will be favored. So you can see what they did here, right? Same thing as before. You deprotonate, you get the alene intermediate. And then instead what we were seeing before is this dotted line here, but they introduced a silyl group, a bulky silyl group, which is actually sterically congesting that proton shuttle. So instead, the reaction is undergoing electrophilic attack with an aldehyde here, and the oxygen is actually deprotonating the amine. So this is the slow reaction. This is the proton shuttle that we saw before, but because it's sterically congested, this alcohol formation is actually going to be favored just due to the steric bulk that's restricting that proton shuttle. So that was what they expected, but unfortunately that's not what they saw. So again, they expected this product, but what they actually saw was cyclicization, and they got a mixture of these two compounds. So based on the NMR, they actually did form this as an intermediate, but further reactions were going on with the alcohol and the alkyne that were kind of driving the cyclicization. So this was formed as an intermediate, but they couldn't stop at this step, and they were getting these cyclic compounds. So kind of interesting, but while this wasn't formed as a product, this being formed as an intermediate it's promising at least. This is kind of cool here. So there's been a couple groups that have worked with these catalysts. So I think we talked about the first two reactions. This bottom one is another one that I didn't go too far into. But what they saw was, for each of these reactions, there was a vast difference in the optimal ligand that they saw. So you can see for this reaction, the optimal ligand was this big ligand here. And then for these two, it was a lot smaller, not fixed amines instead of free amines. So I just thought it was pretty cool that, these reactions, what they're forming, the optimal ligand that they wanted in their catalyst was so vastly different. A lot of the cases, like for example, in this top one Wang's work, they actually used both of these catalysts below and they got no product formation. So, despite it being in the same location and deprotonation, it just goes to show that the ligand is super, super important in the catalyst. So trying to find that ideal ligand to drive your reaction is important. So now diving into my actual research. So building upon the work by Li and Wang, similar CH activation catalysis will be attempted with an electrophilic fluorine source. So in the one work, they used aldehyde as an electrophile. I'm kind of focusing more on using electrophilic fluorine to create a propargylic carbon fluorine bond. But yeah, so, and then another thing I'll get into is the use of steric effects to kind of provide asymmetric catalysis, which is an exciting field that I will talk about. So as I discussed, so the original work was direct propargylic carbon-carbon bond formation. The substrate underwent carbon-hydrogen activation, followed by nucleophilic attack of the allene to the electrophilic aldehyde to form that intermediate that they had. So they saw cyclicization through the alcohol. If you are able to directly halogenate, cyclicization would not form. At least it should not. Cyclic fluorine compounds are not, to my knowledge, existent. So it kind of would hopefully trap at that intermediate and not form a cyclic compound that we saw in the previous work. So I've kind of discussed the electrophilic fluorine sources. So here's two of them, the more popular ones. So select fluor and NFSI. It doesn't generate a full F+, but the fluorines on here both have electrophilic character. So they are able to be attacked by a nucleophile. So they're a little uncommon because when you think of fluorine, you usually think of anions. But in this case, these do exist and they're actually quite stable compounds. So there is no current reportings of catalytic propargylic CH fluorination. And also fluoropropargylic motifs are very rare in organic synthesis. There's very few recorded products. So this makes it, again, a quite unknown but exciting kind of field to work with. So these are kind of the expected products that I have proposed. The use of different R groups might help drive catalytic reactions. So we can replace R with an electron withdrawing group or an electron donating group on an aromatic ring. And then also using just alkyl groups as well. I proposed 6+. I feel like anything less than that would be pretty volatile as a product. So I'm kind of working with larger alkyl chains just for that. And then the importance of the TBS group. This is kind of acts as a protecting group in a sense. So as we talked about, it sterically prohibits the proton shuttle that we saw in the one research. And then it also ensures that there's only one propargylic carbon site right here, and there's none on the TBS group. So that's kind of the purpose of that. So here's the full proposed mechanism that I've worked up. So you have your activated catalyst here, addition of a alkyne, you get your nu2 coordination here. Then you have your intrinsic base that will deprotonate that propargylic hydrogen. That's going to give you direct coordination to this carbon through the gold, form this allene intermediate, which can then decoordinate, and then this system here can attack a F+ source, an electrophilic fluorine source. And then addition of a base to deprotonate the amine will regenerate the catalyst and give you a monofluorinated propargylic product. So that's kind of the proposed mechanism. So why monofluorination over difluorination? A couple of reasons why I believe, or I propose that monofluorination will be favored. So once it's fluorinated, the alkyne is less electron dense due to carbon fluorine polymerization. Therefore, there's going to be less attraction for the gold to bind to that as opposed to the original alkynes that are used. Fluorine is also bulkier than hydrogen, so it may restrict deprotonation of the other propargylic hydrogen for the cycle to go through twice. So you can see the first step I expect to be slow just because I don't think coordination would be favored with this alkyne over the other alkyne. And then again, this fluorine being here may restrict this deprotonation, so you're getting even slower. I don't think it's impossible. I think that over an extended period of time, some difluorination could happen, but I wouldn't expect it as the major product. Also, a very important thing is using one equivalent of the electrophilic fluorine source compared to the alkyne to kind of restrict this difluorination. Difluorination isn't the worst thing. If this happened, I would still be, I'd be surprised, but it would still be interesting, I should say. So I'll go into the methods a little bit. So besides the catalyst, what's kind of going on here? So you have the alkyne. Again, the various functional groups with sp3 hybridized propargylic site. Here's the synthetic route to protect these. It's pretty easy. You take your terbutyl dimethyl chloride and your terminal alkyne, deprotonated with butylene, just one-step process, you purify it. So these are the two that I'm going to start with, I'm proposing. So sodium barf, what that does, it's a chloride abstractor. It just simply is going to activate the catalyst. So I usually use that in a 10% load as opposed to a 5% load from a catalyst. Obviously, the electrophilic fluorine source, which we talked about, so SelectFluor and NFSI are the two that I propose to use. A base to regenerate the amine on the catalyst. I'll get into that a little bit more. And then the solvent, most of the research that I've went through used 1,2-dichloroethane, which is basically DCM, but a little less volatile. So it dissolves everything pretty well. So that's kind of the proposed solvent there. All the work is done on small scale reactions. The reason for this is there's no point in developing a gram of catalyst if it's not going to work. So as far as the research goes, I usually use 5% catalyst load, which is about 2 milligrams or 0.0025 millimoles, and then about 0.05 millimoles of the alkyne. And all the reactions are done in nitrogen atmosphere, usually heat in an oil bath to about 80 degrees for about 16 hours. But again, this is the small scale I work on. So about, 0.5 mils of solvent. But that's just because, there's, like I said, there's no point in making an excessive amount of catalyst if you figure out it's not going to work pretty soon. So basic experimental optimization stuff. So instead of sodium barf, maybe some sort of silver salt could be used as a catalyst activator. Instead of 1,2-DCE, trifluorophenyl might be used, similar catalyst, or THF, similar solvent. So that's something else looking into. And then obviously like using more or less time or higher or lower temperature. So these can all be adjusted. Luckily, you can throw a bunch of these vials in an oil bath, so I can test a bunch of these at the same time. So unfortunately, because the research is so new, these catalysts are not commercially available. So you have to synthesize them yourself. So these are the 3 ligands that I propose to start with. And you can see, so you start off with just a Suzuki coupling reaction to get this product here. Then you just do a reduction of sodium borohydride, and then there's 2 different types of methylation reactions. You can go from this intermediate. And then phosphonations is going to get you these 2. This one down here is a little different. Again, you start with the Suzuki coupling. You have your primary amine, and then you actually do a reaction with, I believe it's 1,5-dibromopentane, and it's actually going to create this cyclic ligand here, and then you phosphonate that to get this product. So these are the first 3 ligands that I want to catalyze and work with. So a big difference between this work and the other one is regenerating the catalyst. So in the first 2 works that you saw with the proton shuttle and the alcohol formation, the substrate was deprotonating the catalyst. Of course, fluorine can't deprotonate the catalyst once it's already attached. So introduction of a base is important. Through some pKa calculations, I've estimated that this amine is about 5 to 6, the pKa. So I would need a base that has a higher pKa in order to deprotonate that, or at least get it within equilibrium. Because higher pKa means a stronger bound hydrogen to the base. So an inorganic base like potassium hydroxide might be used. An organic base like triethylamine has a pKa of 10.75, so that would be favored. Another kind of cool one is this product here. It's called a proton sponge. Again, it's an organic one, and it can basically trap a proton. The pKa is pretty high, 12.34, so that hydrogen is probably not going to go anywhere. But again, the type of base used, that's another kind of aspect of my research. So characterizing the compounds. So multinuclear NMR spectroscopy, mostly hydrogen, carbon, phosphorus, and fluorine, are going to be used for mechanistic and catalytic studies. X-ray crystallography, mass spec, IR is also helpful for characterization, although won't be used as much. The very little research I have found on propargylic fluorides are anywhere between -150 to -210 ppm on the fluorine NMR. This one I found here is probably the closest to the products I'm trying to make. So you can see it's around, -175, -180. It's hard to see here, but if you zoom in, it's actually a doublet of triplet, which makes sense because you have J1 coupling to this hydrogen, J2 coupling to these two hydrogens. So the fluorine NMR is going to help out a lot too, because if you see a doublet of triplets, you have monofluorination. If you just see a triplet, that kind of indicates that you have difluorination. So this is kind of where I would expect the range, -150 to -210 for the characterization. But like I said, with the lack of these type of compounds being made, it's not for sure. Another kind of side project, speaking of characterization, this is an alternative route I have proposed in order to make the product. So it's not catalytic, it's pretty harsh, it's not functional group tolerant, it's pretty hazardous. So this is definitely not an ideal pathway, but if I'm finding out the original pathway is kind of tricky, I can try out this one in order to get the product. That way I can characterize the product, see if it's volatile. It's possible you throw this stuff on the rotovap and it just shoots right off. But if you look at the pathway, right, you're working with a Grignard, which is, a little hazardous, and then Bewley, which is a little hazardous, and then methyl dast is also pretty hazardous. It's big explosive potential. So doing this pathway, you're definitely going to have your coffee in the morning and make sure you know what you're doing. But I still think this is important, especially if there's struggles generating this product. It might be because it's a little more volatile, or just being able to get NMR X-ray data for this product would be super helpful in the research. So mechanistic studies. So you can do various homonuclear NMR studies to analyze and confirm the reaction mechanism. In this case, this is where phosphorus NMR is going to really, really come into handy. And I have a proposed mechanism, but it's always nice to be able to prove that mechanism. So the phosphorus NMR, based on previous work for this phosphorus, for these catalysts, it's about 60 to 65 ppm. With coordination to the alkyne here, you now have a cationic gold complex. So I would expect the shift to be more shielded. So you're going to get less than 60 to 65. And then in this case, you have direct coordination to the alkene here. So I would expect more shielding or a higher chemical shift than 60 to 65. So if I can trap these intermediates and get NMRs at each one, and I'm seeing those expected shifts, that might be able to help prove the mechanism that's actually going on. So this is another project that I'll definitely be working on through my research. And then I want to end it off with another super exciting aspect of this work, and that is stereospecific monofluorination. So introducing bulky substituents can help facilitate stereoselective deprotonation through steric interactions. It's kind of hard to visualize in this sense, but what you're getting is these bonds aren't actually this long. What you're actually coming is they're coming out of the page and reaching down over. But what you can see here is, say this R group is something bulky like an isopropyl group. It's actually restricting deprotonation of this specific hydrogen through steric interactions, which means you can only deprotonate the one hydrogen. So that is driving asymmetric catalysis, giving you a stereoselective product, which for pharmaceuticals, especially, stereospecificity of products is super, super important. Here's kind of another visualization on it. So different groups and positions and stereochemistry of the backbone can be developed to enable stereoselective deprotonation. Again, so around here, I didn't draw the full diagram in this one, but again, you have the sterics from this isopropyl group on this hydrogen, making it only able to deprotonate this specific hydrogen. And then as you see, as it goes through, then you have only fluorination on the dashed bond as opposed to the wedge bond. And again, if you just have this one dashed instead, then it could flip the stereochemistry. So development of ligands that may be able to drive stereospecific monofluorination, that's kind of something down the road that I definitely want to take a look at. So what's the point? What's the whole impact of this work? As I mentioned before, there's no current reportings of catalytic propargylic CH fluorination. So this would be the first reporting of it. There's also a lack of characterized fluoropropargylic compounds, as I mentioned before, so you can better understand the nature for future experimentation. It's also important to provide a one-step stereoselective monofluorination through gold catalysis. That's going to save you money, time, and reagents. I pitched that other pathway to the product, and you can see it's a lot harsher as opposed to a one-step catalytic method that I'm trying to do. And again, it's much more environmentally friendly. There's lack of heavy metals or fluorinated byproducts. So there's no HF that's going to be formed like if you're using F2. Gold is a pretty benign metal compared to some of the other ones. So yeah, it has some good environmental impacts and cost impacts as well. So fluorinated organic molecules are extremely important for material science, pharmaceuticals, agrochemicals, and many other industries, as I mentioned. So even more future work is after propargylic fluorination, you can undergo deprotection of that silo group and then undergo alkyne functionalization to develop a whole mass of brand new fluorinated molecules. As you can see here, if you do happen to get the product, you can deprotect. So either throw a hydrogen on here, another functional group. And then once you have this, alkynes are super easy to functionalize in so many different ways, right? So you can form ketone products, alkene products, supersaturated fluorine products, just alkyl products. So that's kind of the whole point of forming these propargylic fluorine bonds, is you can do so much with that alkyne in the future that, the synthetic pathways are just, through the roof. There's so many different options that you can do. So kind of to summarize my presentation here. So the whole goals of my research, number one, the main one, is to develop an optimal bifunctional gold catalyst capable of monofluorinating propargylic carbons through one-step carbon-hydrogen activation. As you saw before, there is so many different ligands that can be used, and changing them just the tiniest bit might totally shut down the reaction. So for this reaction specifically, being able to find that exact ligand for that catalyst that's going to drive this reaction, it's going to take a lot of research, but super important. So synthesize and characterize new fluoropropargylic organic compounds. Like I said, there's basically none. It's super hard to find any references. So being able to form these and then characterize them just for scientific impact, I think is super important. I talked about utilizing steric interactions to drive stereospecific monofluorination. As I said, it's as easy as throwing in big bulky groups that are going to block one hydrogen over the other. So being able to do that would be huge. And then I talked about further activating the alkyne to develop mass amounts of fluorinated organic compounds. checking functional group tolerance with that CF bond, stuff like that. That's also some future work that I want to get done. And then, of course, expanding the field of organofluorine chemistry. As I mentioned, growing industry. So super exciting stuff there. But yeah, that is basically the gist of my research and everything I'm hoping to get done in the next little bit. So thank you guys for watching. And then I have my massive references. But yeah, thank you guys. And yeah, I hope you have a good day.